Okay, now up till in the last three lectures we studied through the scatter plots how we assign the degree of correlation, because the correlation is actually something, or the coefficient of correlation is something that explains the strength of the relationship between the two different quantities. And with the help of the scattered plot, we just learn how to understand or how to analyze the degree of correlation, whether it is a strong correlation between the two quantities or whether it is a weak correlation between the two quantities. And then we understand how to obtain the best fit. And we just said that if the best fit is coming in the form of a straight line, then we call that a regression line, and we are going to say that such correlation is a linear correlation. And if, for example, if we say that the scatter, in order to maintain a best fit in the subjective scattered plots, and if that best fit is coming in the form of a curve, then we call it a regression curve. And in that case, we are going to say that the correlation is not linear in nature. It is a non-linear correlation between the two quantities. That is not the part of our lecture. So if the correlation is, in case of a best fit, it is representing a linear correlation, then in order to understand the degree of correlation numerically, we are going to use a terminology that we already we have discussed, that is called the coefficient of correlation. And in case that if we are just dealing with a sample of data, and we are concerned to take out the coefficient of correlation in that case, then we represent a term small r for it, that was this. And if we are dealing with a data comprising the entire population, then in that case we are calculating the coefficient of correlation, that it is represented by rho, that was this. So over here we are concentrating on the sample coefficient of correlation, because whatever we study for the first time, we try to study on a restricted boundaries in a restricted area. So we just focus on a sample of data over there. So once, let us have a look on an example, and we just try to figure out what kind of relationship is over there after having a look on the data. We just draw a scattered plot. After that, we are going to assign the best fit. If the best fit is coming in a form of straight line, then we will say that the correlation between the two quantities is a linear correlation. After that, we are going to approach to the calculation of coefficient of correlation in order to obtain the strength of correlation. So here we go, relative example, and here we go. And this question says that there's an agricultural research organization tested a particular chemical fertilizer, and in order to find out whether an increase in the amount of the fertilizer used would lead to a corresponding increase in the food supply. So here they have just given us particular restricted data, okay? So the fertilizer is mentioned in the pounds, and the bushel of corns over here representing to each and every fertilizer quantity so used here. So it is this, and okay, now up till here we have to assign that which quantity is going to be considered an independent quantity and which quantity is a dependent. You see, the quantity of fertilizer is responsible in the increase and decrease of the bushels, or the increase or decrease of the production. So here this is an independent variable that we are going to use in x, and this is the dependent variable that we just say y, okay? And this is the ordered pair that we are going to plot on a graph, on a 2D plane, and then we are going to see the nature of the scatter points out there. Then we are going to find out the line of the best fit. Then after seeing the nature of the best fit, if it's coming out to be a straight line, then we are going to determine the coefficient of correlation, because you see there are several methods of determining the coefficient of correlation. And if the relation is linear, then we are going to use those formula which are used to determine the linear correlation coefficient. All right, so let's find out, let's plot the subjective ordered points on a plane coordinate system. So here I've just drawn the scatter plots of the given set of data, representing the bushel of corns so produced by using a particular amount of the fertilizers in pounds. So here you can see that this scatter plot comprising 6 ratings. So it is 7 ratings, sorry. So you can see that you are having quite concentrated band, and it is not much broad, and it is moving uphill to right. Okay, so this is representing quite and it is quite concentrated, and it is moving uphill to right. So this is a strong correlation, and it is showing the direct proportionality between these two quantities. Means if the fertilizer is increased, then this is going to represent the increase of the bushels of the corns, or increase in the production. So, and if you are using less amount of fertilizer, then it is going to affect, or it is going to decrease the production too. So there is a direct proportionality here. So the correlation is direct and it is strong. So therefore it is a positive direct correlation. So this is it. Now once we have assigned a direct correlation, it is known to us. Now let us find out the best fit. What would be the best fit shape we are going to get? So if it come out to be a straight line, then we say that the best fit is a straight line. So the correlation is a linear correlation in nature. Then we are going to use a linear correlation coefficient formula in order to solve our problem. So let's draw a line of the best fit. Okay, now I just tried to maintain a best fit, and I come to know that the best fit is coming in form of a straight line. You can see that the majority of the points are lying on this line, and the remaining ones which are not lying are at least close to it quite much. So in my view, this is the line of the best fit, and it is a straight line. So the subjective relationship between the two quantities, the bushel production and that of the fertilizer, it is linear. So now we are here to calculate the coefficient of the linear correlation R in order to determine the degree of the correlation, and in order to determine the strength of correlation. All right, though the scattered plots diagram is explaining us the degree of the correlation, that it is a positive and strong direct correlation, but we want to figure out this thing numerically, so that's why we are using the coefficient of correlation. Now, as I told you already, that we are having several methods of calculating the coefficient of correlation, but instead of in case of linear value of R, we prefer to adopt the formula of Karl, so introduced by Karl Pearson, who was an English mathematician and a biostatistician. So we are going to use the formula so introduced by him. That's why it is on his name. So we are going to use that formula. So for that purpose, let's have a look to the formula first, and then we are going to figure out the numerical. So this is the subjective formula of the Karl Pearson, and also we call it Pearson method of coefficient of correlation, PMCC. Okay, so here you are given the particular quantities, and in the column of our question, we have to introduce few more columns related to our summation of x, summation of y, summation of x square, summation of y square, and summation of xy. Okay, so overall we have to make 5 more columns, and then we have to substitute the subjective values in the formula, and then we are going to get the value of R. And on the value of our R, we are going to assert the degree of correlation between the two quantities. Okay, so let's make the subjective columns. Okay, now here I have just made the subjective columns. 2 were already made, and 3 more I have to make here, and I've just done that. So over here, as I've already mentioned, that this quantity is the independent one, so it is x, and this one is the dependent one, so it is y. So I just sum up all these values, and I just got summation of x, and same thing I have done over here in order to get the summation y. Now I have to take out the square of my x quantities. Okay, if it's 2, then the square of 2 is 4, and so forth. I have to do the remaining ones. So let's finish up this column. Okay, now once we have just accomplished these 2 summations, and we were up to maintaining the squares. So when we find out the squares of all the x values, we get this. then we sum up all these values, we get the summation of x squared. The same thing we are doing with the y squares. We just take out the square of the y values. 4 into 4 give you 16 and so forth. It's a basic maths. So we just find out all the subjective y squares, we sum all these values, we get the summation of our y square. After that, we have to find the xy, means we are taking the product of these corresponding xy values. 2 multiplied by 4, 1 multiplied by 3, and so on. So we just got all these subjective answers. We just sum them up, and we just got the summation of xy. So these are the values. Now we are going to substitute these answers in the correlation coefficient formula represented by the Karl Pearson. And here you can see that n is representing the number of the data pairs. So you can see this is the data pairs because every point is expressed in the ordered pair of two tuples, because there is the involvement of two quantities that we are analyzing here statistically. So here you can see that there are 7 pairs, so n is 7 here. Okay, so it is 7 in a small sample, so we have to insert all these answers in this formula, in this PMCC formula. Okay, and we have just done that, and it comes out to be this. Okay, you have simply substituted all these corresponding answers, and you just do the basic maths. You just find out that the value of r is 0.811. Okay, you can have a look. Okay, so 0.811, very close to your 1, and therefore this depicts that this is, and it is a positive answer, so it is greater than 0. So it is representing a direct correlation, means if the one quantity is increasing, the other one is also increasing. So this thing represents a direct correlation representing a positive slope. So whenever you're having a positive slope, then this thing tells that your r is also going to be positive. Okay, it doesn't mean that the slope values are. R is not a slope value. Slope is the coefficient of the regression line, and r is something different, but it is depending on the slope formula, slope value. Okay, if the slope is positive, so this thing is representing a direct correlation, a positive correlation, and the r is also definitely going to be positive. It doesn't mean that r is equals to m. No, it is not like that. M is something different. M is the slope of the regression line. So M is the coefficient of the regression line. R is the correlation coefficient. But there is a relationship between these two quantities that we are going to discuss in some other lecture. So presently we have to focus just on the behavior. So scatter diagram, whatever it tells us about the behavior or about the degree of the correlation, same thing has been explained by the value of R that we have calculated numerically. So as r is coming out to be 0.81, so it is approximate, so it is 81.1%. This is a strong percentage. So this shows that there is a direct correlation between the fertilizer and the bushels. So if you increase the fertilizer quantity, so the production of the food production is also going to increase. So it is a positive, strong correlation. So it is a correlation of high degree. That's what it means. So I hope you have understood, and we'll discuss the standard error of estimation in the next lecture.